as far as I'm concerned, these two things go together. So I've put them under the one heading here, even though they're separate things in your notes. We're really dealing with the same thing. So let's quickly go back and have a think about what we did last time. And last time we said, if I have a right-angled triangle, then we defined, for this particular angle theta here down at vertex A, we said that the sine of theta was the value of the ratio of the opposite over the hypotenuse. Likewise, we said the cosine of theta was the adjacent over the hypotenuse, and the tan of theta was the opposite over the adjacent. And we had the reciprocal ratios as well, and we saw last time that no matter what right-angle triangle we had, if it had that angle of size theta, these ratios are constant. And essentially it took me 2 hours last Thursday to say that. Okay, and that's it, that's all I said. So, clearly if I have a right-angled triangle, so I've got 90 degrees here, and the sum of the angles in a triangle is 180, these remaining angles have to be less than 90. So as that stands, by thinking about right-angled triangles, these trig ratios only apply for angles between 0 and 90 degrees. What we want to do is to generalise that, to make things work a little bit better. Now, I have read a bit of history of mathematics, and I actually don't know who it was thought up this redefinition of the trig ratios, but whoever it was pretty darn smart, because the idea of redefining our trig ratios in terms of the unit circle, which I'll talk about in a minute, turns out to be super, super powerful. Really, really good idea. So as I said, I should go back and make another attempt now to find out who actually did that, because they deserve a pat on the back. Okay, so let's have a look at what they did. So it says, consider the unit circle. By the unit circle, I mean the circle of centre, origin, and radius 1. So centre, 0, 0, and a radius 1. That's what I mean when I say the unit circle. And in the first quadrant, so let's move over. In the first quadrant, we see that the coordinates of a point P on the circle that makes an angle R. So let's go through all of this. We need to define a few things first. So let me put that one up there. Let's make sense of that sentence. So the first quadrant is this quadrant here. This is the first quadrant. And I guess one way of describing the first quadrant would be the coordinates of a point have a positive x coordinate and a positive y coordinate. That's one way of describing your first quadrant. Another way is to say, whoops, I'll go to this picture here, is that the angle is between 0 and 90. So I can do it in terms of coordinates, or I can do it in terms of angles. So I can say that the angle is between 0 and 90. That refers to the first quadrant, and that's that little part there. So let's do the other quadrants while we're at it. So by convention, we agree to go around counterclockwise. So first quadrant, second quadrant, I'll put it here, third quadrant, and fourth quadrant. And in this one has a negative x, positive y. Third quadrant has a negative x and a negative y. And the fourth quadrant has a positive x and a negative y. In terms of angles, the first quadrant goes from 0 to 90. The second quadrant goes from 90 to 180. The third quadrant goes from 180 to 270. And the last quadrant goes from 270 to 360 degrees. So that's our terminology sitting here. And I guess the other thing that's interesting, you can see here I have my unit circle, centre 0, 0, radius 1. So let's just say that's the unit circle. And the interesting thing about the unit circle is that I know its equation. It's x squared plus y squared is equal to 1. Yeah, I can fit it in here. X squared plus y squared is equal to 1. Okay, so the sentence says, consider the unit circle. Here it is. In the first quadrant, so we're just in this part here, in the first quadrant. We can see that the coordinates of a point on the circle, so here I've drawn a point on the circle that makes an angle theta, and perhaps I should come back here and just fill this in to make this clear, makes an angle theta, and I will say here, with respect to the positive x-axis. And we're going counterclockwise. Counterclockwise in there. So if I can put that back here, with respect to that positive x-axis. So here's my angle theta, here's the positive x-axis, and I'm going counterclockwise, theta degrees, and I draw the radius, and there's my point P. So it says, the coordinates of that point will be, and on this page it says up there, cos theta, sine theta. So let's see how that comes into place. So, here's my point P, drop a perpendicular down to the x-axis, and you can see I have a right angle triangle sitting there. And so, for theta, this side here is the opposite side. That's the opposite. And let me, for the sake of making life easier, so I'll call that y naught. Likewise, this side on the right angle triangle is the adjacent, and let me call that x naught. And the hypotenuse here, the hypotenuse is that side, and it has length 1. So point P here has coordinates x naught, y naught. That length and that length describe where P is. Now, with respect to our right angle triangle, here I know that the sine of theta is the opposite over the hypotenuse. So y naught over 1. I now rearrange that, make y naught the subject, and that tells me that my y coordinate of point P is in fact sine theta. Likewise, if I come over here, the cosine of theta, cos theta is the adjacent over the hypotenuse, so that's x naught over 1. Make x naught the subject, that says x naught is cos theta, so the sides of the x coordinate is in fact cos theta. So given that the radius makes an angle of theta with the positive x-axis, I know the coordinates of point P. It's cos theta and sine theta. So, as I said, some very smart cookie saw that and thought, okay, that's pretty cool. And then said, well, I can even do cleverer things. Why don't I, if I have P over here, say the x-coordinate's cos theta and the y-coordinate's sine theta? Or if P's down here, say the x-coordinate is cos theta, the y-coordinate is sine theta, and so forth. So has turned the whole thing around. In the first quadrant, we went from the right angle triangle to the coordinate. What we're going to do now is we're going to turn it around and say the coordinates are the sine and cosine of that particular angle. So I don't need the right angle triangle at all. And as I say, how somebody thought that up in the first place, I've got no idea. But having done so, it turns out to be really, really useful. Okay? So we can use this observation as the basis for defining, that's the important word there. We now say this is the very definition of sine theta and cos theta. So we can define the trigonometric, now ratios is probably not quite the right word there because we have no longer got the triangles. But I'm going to continue to call them the ratios until I introduce the word function, next lecture. So by defining the trigonometric ratios for angles of any magnitude. So here it is, down here. Let's make this box very important. For any angle, let the point where the radius of the unit circle makes with the positive x-axis be P. Then we define the sine of theta to be the y-coordinate, the cos of theta to be the x-coordinate. And to get the tan of theta, we have to use one of our trig identities from last time. We said last time the tan of theta was sine over cos, so we will now make that the very definition of tan theta. And so that is our new, improved vision of the trigonometric ratios. The beauty of this new definition is that everything that we learnt before still holds, right? Because here we were in our right angle triangle, everything worked in there. So we don't have to unlearn anything, we just have to add to our concept. And that's nice.
Does that only work on a circle with radius 1?
Yes. Yes, the unit circle, that's correct. We can work out the coordinates of a point on a circle of a different radius. It turns out to be r cos theta and r sin theta. But we're defining the cos and sine, and so the definition does assume that the circle is of radius 1. Yep. So there it is. I don't need to say anything more for today. That's today's lecture. But I will go through and do a few more examples, okay? But this is it. This is it, all right? Important thing. Okay, so let's try and make some sense of this box here, and let's work with an angle that's not in the first quadrant. Okay, so I'm going to use this terminology consistently from now. So perhaps this is the page that I will need to keep on top for the rest of the lecture. Page 2, important page. Okay, so imagine now that we have a third quadrant angle. So if theta is a third quadrant angle, or alternatively I might say if P is in the third quadrant. Oops. Okay. So in other words, theta is somewhere between 180 degrees and 270, going counterclockwise from the positive x-axis. So that puts us in here somewhere. Then I would say that the sine of theta is the y-coordinate of P. Now, sitting down here, there's the y-coordinate of P. So here, this is the, I might actually say, that is sine of theta. There. And the important thing to realise here is that the sine of theta is between 0 and -1 in here. So in this case, sine theta is in fact negative because this y-coordinate is negative. So I can say, where will I put it? I'll put it over here. So I'll say, note that the sine of theta is somewhere, whoops, got to go the other way. -1 is less than sine theta is less than 0 in that case. The y-coordinate is negative. Likewise, the x-coordinate of P is going to be the cos of theta. And so likewise, in the third quadrant, the cosine of theta is between 0 and -1 So negative, I'm not too sure what it is. This one looks like it's getting here close to -1, but it's not -1. It's between 0 and -1. So you can see, sitting in here, if I'm in the first quadrant, the x-coordinate and the y-coordinate are both positive, so sine and cos will be positive. In the second quadrant, the x-coordinate is negative, so cos theta is negative, but sine theta is positive because the y-coordinate is positive. In the third quadrant, both sine and cos are negative. In the fourth quadrant, the cos is positive because the x-coordinate is positive, but the sine will be negative in there because the y-coordinate is negative. And I guess I may as well do it while I'm here. The other interesting thing is I get the tan of theta by dividing the sine divided by the cos. So if I've got a positive divided by a positive, so the tan of theta will be positive in the first quadrant. Whereas here, the x-coordinate is negative, the y-coordinate is positive, so tan will be negative, tan will be positive, tan will be negative. And there's a little standard mnemonic that is quite often used. Yep, I think I hear someone whispering it already. You put an A, S, T, C in there. All trig ratios positive. The sine is the only one that's positive in the second quadrant. Tan is the only one that's positive in the third quadrant. And cos is the only one positive in the fourth quadrant. And you can make up whatever words you feel like to go with that. I mean, when I was at school, it was all stations to casino, because I actually lived in casino when I was a young whippersnapper. But you can, I don't know, all stations to Cardiff, all stations to Central, make up something, okay? And that will work. Sorry? All stations, you're not going to Cardiff? All right, make up whatever you feel like in there. But that's just a little thing to help you remember. Mind you, you should never really need to remember that, because you just say, look, x-coordinate, y-coordinate. So, yeah, there's a mnemonic, you don't really need it. The other interesting thing that I can show you here is that we can relate this sine theta and cos theta of this third quadrant angle to a first quadrant angle. And sitting in here, if this angle is theta, then that angle sitting in there will be theta minus 180. Agreed? So that angle, if I can squeeze it in, I'll say it's theta minus 180 degrees. That's that angle there. Okay? So sitting in here, here's a right angle triangle. And I said to you, our new definition completely encompasses the old one. So I should be able to ignore the axes and everything and just say, look, here's a right angle triangle. Everything that I learned about the trig ratios should work. So, for example, the cosine of this particular angle here is the adjacent over the hypotenuse. Now the hypotenuse here is 1 again because the circle has radius 1. So I can say that the cos of theta minus 180 degrees is, what did I call it? I might call it just x naught again here. If I call the value of the, perhaps I should draw a picture a bit here. Let me, where do I want it? I'll put it down, here's the spot to put it. If I've just got this triangle sitting here, then I'm going to call that side length x naught and that side length y naught, that side there 1. So cos of theta is x naught on 1, but in this case, I know I've got a negative value in here, so I'm going to call it minus x naught to make sure I've got a negative x value in there. This triangle just said, look, that's a distance. Whereas in this one here, I've actually got to take into account where I am on the plane. So this will be x naught on 1. So x naught will be, in here, minus the cos of theta minus 180. And so I can say x naught is the, so I can say here that cos theta, in here that's the x coordinate, will be the minus of theta minus 180 in there. And perhaps, I mean that doesn't look very interesting, but if I redraw this triangle over here, I go there like that. That angle there is theta minus 180. So is this angle here. That's also theta minus 180. Sitting in there. And now I have my normal right angle triangle. If I call that there x naught, or x naught dash, x naught will do, that's y naught. I can get this value here in terms of that value there. Clearly it's the negative of it. So I can get the cosine of a third quadrant angle in terms of a first quadrant angle, just by drawing the appropriate right-angled triangles. And likewise, I can do the same for sine. The sine of theta minus 180 will be this distance here, whatever you like to call it. It's y naught on 1. So y naught is the sine of theta minus 180, and then, therefore I can say, this is what I should have done. That should have been a plus there. I'll do it this is much better. So here, so sine theta, now y naught is that, but I know this is negative. So sine of theta is minus the sine of theta minus 180 in there. I can put that like that. So there's a relationship between our third quadrant angle and what happens in the first quadrant. So the important thing is, get yourself a right angle triangle, work out the magnitude of the sides, and then you can work out by which quadrant it is, whether it's negative or positive. That's the simplest way to explain it. All right, I've made a simple thing look difficult there, but hopefully if I can do some examples, I can make it clear. So let's do some examples sitting in here. Okay, so start off. Let's work out. Find the exact value of sine of 0 degrees. So it says, draw yourself a radius of the circle that makes an angle of 0 degrees with the positive x-axis. And so that will be right there. There's my radius, 1, and there's my point P sitting right there. So this is, I'm going to do A and B on the one picture sitting here. And I know the coordinates of P there. I can see it quite straightforward. That P has coordinates 1, 0. X is 1, Y is 0. And so the sine of 0 is the Y coordinate of P. So the sine of 0 degrees, that's supposed to be 0, clearly is 0. That's the Y coordinate. That's the Y coordinate of P. Likewise, cos 0 is the X coordinate of P. And so that is 1. So as you can see, there's no triangle sitting in there. So this is very definitely using our new definition. But our new definition works nicely. If you think back here, in this right angle triangle here sitting in the first quadrant, and you made theta and theta get closer and closer and closer to 0, then the adjacent over the hypotenuse are getting closer and closer to being the same. And so as this gets closer and closer to 0, the cos is getting closer and closer to 1. And so the fact that at theta equals 0 equal 1 makes sense sitting in there. Okay, let's do the next one, 90 degrees. So, our first task is to draw a radius that makes an angle of 90 degrees with the positive x-axis. So I go round to there, That's 90 degrees. So here's my radius, sitting there, and my point P now sits up there. There's the point on the circle that makes, or well, the radius to that point makes an angle of 90 degrees with the positive x-axis. The coordinates of that I can read straight off. It is 0, 1. And so now I know the sine and cos of that angle. So this is C and D that I'm doing here. So the sine of 90 degrees is the y-coordinate of P, and the y-coordinate of P is 1. So the sine of 90 degrees is 1. Likewise, the cos of 90 degrees will be the x-coordinate of P, and the x-coordinate is 0. So cos of 90 is 0. So that seems reasonable, doesn't it? That's doable, is it not? Yeah? I hope so. When we come, so these cases were quite easily doable because we could read off the coordinates straight away. When we get down to E and F, the coordinates aren't so obvious. So we have to do a little bit of work. So let's go down now and do E and F. E and F. So it says, I want 150 degrees. So I come around, 145 is there, so this will be about here, something like that. So there's my point P. That angle from the positive x-axis is 150 degrees. I've come around, and there is my point. I can't read off the coordinates of that straight away. I'm a little bit flummoxed there. So I will have to do some work to work out what those coordinates are. Now, what I could do, I can do this two ways. But what I can do is I can actually form a right-angled triangle here, and I know this angle in here because it's 180 minus 150. So that angle in there is 30 degrees. And so I can extract out that triangle and just work with that triangle by itself, irrespective of the axes whatsoever. So I could do this. I could extract out that triangle. That angle is 30. That's your right angle there. And let me just for the moment call that y0 and x0. Now, I know that the sine of 30 is the opposite, which is y0 over the hypotenuse, and the hypotenuse is 1 because this is a circle of radius 1. So y0 over 1, so y0 is sine of 30 degrees. We know the sine of 30 degrees. We saw that last time, and we had it from one of our special triangles. I don't know if you can remember the special triangle that we had, but it had radius sides 1, 2, this was 60, that was 30, and that was the square root of 3. And so the sine of 30 is a half. So that tells me in here that this must be a half. So that's the length of this side over here, and so that is the y-coordinate of P. So I've worked out the y-coordinate of P. It's a half. Let me also work out the x-coordinate of P. So I'm going to work out this length here. And I have the cos of 30 degrees is x0 on 1. So x0 is the cos of 30. And over here, the cos of 30 is adjacent over hypotenuse. That's the square root of 3 on 2. That's the length. So the x-coordinate of P is minus the square root of 3 on 2, because I've got a negative x-coordinate. I've worked out the length just using this triangle here, but I know this is the x-coordinate. So the coordinates of P are minus the square root of 3 on 2, a half. And so I can now say the sine of 150 degrees is the y-coordinate of P, and that is a half. And notice that it's also equal to the sine of 30 degrees. Likewise, the cos of 150 is the x-coordinate of P, which is minus the square root of 3 on 2, which is the minus of the cos of 30 degrees. Let's just try and make some sense of this picture here. It says sine 150 is the same as the sine of 30. The cos of 150 is the negative of the cos of 30. Now, if I were to work out the sine of 30 and the cos of 30, what I would do is I would draw a radius here where that angle sitting in there is 30 degrees. Let me call that P dash. P dash. And it turns out that this triangle, this red triangle, is congruent to the blue triangle, to this one here, just drawn with a different orientation. That's 30, that's 30, that's 90, that's 90, so that's 60, that's 60. And we see that they have the same y-coordinates, but the x-coordinates are the same distance, but one's the negative of the other. So here again, I can relate my second quadrant answer to a first quadrant trig ratio, which is equivalent to what I did up here. Only here it was a third quadrant. I can relate my third quadrant trig ratios to a first quadrant trig ratio by drawing the first quadrant right angle triangle. That may take some time to sink in, but each time, if you just draw the appropriate first quadrant triangle, you'll be able to work out the coordinates of P. So you work out these distances and then say, okay, it's either negative and positive or whatever the appropriate signs are sitting in there. Okay, so we've found the exact values of 0, 90, 150, the trig ratios, or some of the trig ratios for those particular angles. Let's do some more. Let's do 312 degrees, because that's a good one to do. Now, in these cases, we were able to work out the exact values of the coordinates of P. We can't do that for most angles. We can only do it for angles that are related to 30, 60 and 45, the ones for which we could draw triangles. And so for these ones here, we just use our calculator. So your scientific calculator can work out all of these things for any angle. It's a really, you should be getting more and more impressed with how clever your calculator is. Right? It can do this. You don't have to tell it what it is. Just put in sine 312 and it'll give you an answer. Make sure your calculator is in degrees, though, as you do it. So just use your calculator. The sine of 312 degrees I got to be minus 0.743 to 3 decimal places. So I'll say I used the calculator to do it. Is that what your calculator is giving? Anyone just check that I've read my calculator correct? Yep, cool. And so do also the cos of 312 degrees. And when I did that, I think I got 0.669 to 3 decimal places. Yep. And it says, interpret your values geometrically. Oh, draw a picture. So here's a nice big picture to draw. So, we're interested in 312 degrees. So 90, 180, 270. I've got to go another 30. I've got to go another 42 degrees beyond 270. So, let me see, somewhere around. That'll be 45, so it'll be close to 45. It's about here. Something like that. So we have gone around 312 degrees. I've drawn the radius, and there's my point P. And according to my calculator, it says the y-coordinate of P is about minus 0.743. So across here, that value is minus 7.43. And that seems pretty close to, seems pretty reasonable, doesn't it? Assuming that I've got my angle close to 312. Likewise, the x-coordinate up here is about, so that's approximately that, and this is approximately 0.669 is the x-coordinate of P. Sitting in there. That's our interpretation of those values. The y and x coordinates of the point P on the unit circle. Now I guess while I'm here, if I wanted to relate the sine and cosine of this fourth quadrant angle to a first quadrant angle, the appropriate triangle, if I can put it in, sitting here, would be this one. It would come up to here and across there. If I call that P dash, so this angle is 360 minus theta. So that angle in there is 360 minus theta. And it's saying that the y-coordinate of this point is the negative of the y-coordinate of that point, we could see, but the x-coordinates would be the same, sitting in there. So that angle would be 360 minus theta. And so I could conclude from that picture, for example, so I'll just say as an aside here, that the sine of 312 degrees would be the negative of the sine of, it must be 48 degrees. 360 minus 312 would be 48. So get out your calculator, work out the sine of 45. You should get 0.743 to 3 decimal places. Did it work? What have I done wrong? 48 and 12 looks like it should work. Should be 0.743.
It is right, because it's negative. Yeah.
The sine of 48 should be 0.743. It should be positive. That's right, and that's the negative of this. All right, it's the negative of that. So it should work. You did something wrong. Okay, cool. And likewise, the cos of 312 degrees would be exactly the same as the cos of 48 degrees, because they have the same x-coordinate in there. So there I'm relating the cos of a fourth quadrant angle to the cos of a first quadrant angle. But as I say, to work out the value, just whip out your calculator and stick in the value, and that's it. And as I guess I should highlight, that these are approximate values rather than exact. We can't get the exact values for those particular angles. Now you can imagine, I think, that we've started with theta, we've gone around 90, 180, 270, 360. I could keep going. I don't have to stop at 360. I could add another 90 and go on to whatever, 90 and 360, 450, and keep going, 540 and so forth. So this can just keep going on and on and on. Likewise, I can go backwards. And so if I rotate, instead of rotating counterclockwise, I rotate clockwise, then we call that a negative angle. So we define negative angles to be measured from the positive x-axis, but going clockwise, in fact. So for example, if I were to draw a little one down here, so minus, what have I got? So it says minus 135 degrees, for example. I would start here at x, y, and I would go around here 90 and another 45. So there we go. That angle would be minus 135 degrees going that way. So minus 135 degrees would be the same as going plus 225 degrees. You end up at the same point. So let's just put that in. That's the same as going around this way. 225 degrees. So if you were to find the trig ratios of minus 135, they would be the same as the trig ratios of plus 225. So let's do some. So it says, find the exact values in this case of sine and tan of minus 45 degrees. So let's do A and B in the one picture. And my task is, it says, find the point P whose radius, it makes minus, an angle of minus 45 degrees with the positive x-axis. So that's going to put me, and I'll make it a little bit neater, it'll go through here. So here will be my point P sitting there, and that angle is minus 45 degrees sitting in there. So let me form a right angle triangle sitting in here. And for later reference, let me just go up the top as well. I'm going to later call that P dash. And I guess I can dot this in as well while I'm at it. So here is a right angle triangle, and there's another one sitting there. So I have to find the coordinates of P. So here is a right angle triangle. Let me extract it out. Here it is. Sitting here. That angle now in this, if I'm just considering that as a triangle, is 45 degrees. This hypotenuse is 1 because the radius of the circle is 1. And let me again just call these sides y0 and x0. I'm going to find the values of x0 and y0. So I know, for example, that the sine of 45 degrees is y0 over 1. So y0 is equal to the sine of 45 degrees. And we know, if we look back at our special triangles, that the sine of 45 degrees is 1 on root 2. Now, the other thing it asks for, so I'm getting the sine here, but I need the tan, so I'm going to work out cos while I'm at it, because to get tan I have to go sine divided by cos. So let me do the cos while I'm at it. So here, cos of 45 degrees, according to this, cos is the adjacent over the hypotenuse, so that's x0 over 1. So that tells me that x0 is equal to the cos of 45 degrees, which is also 1 over the square root of 2, according to our special triangles. So I've got the size of those lengths. I now want to go back and find the coordinates of P. And I can see that P has a positive x coordinate and a negative y coordinate. So the coordinates of P are 1 on root 2, that's the positive x coordinate, and the negative y coordinate is minus 1 on root 2. And so here I go. So therefore I can now say the sine of minus 45 degrees is the y coordinate of P, which is minus 1 on root 2. To get the tan, I need the cosine, so let me work out the cosine while I'm here. The cosine of minus 45 degrees is the x coordinate of P, and that is 1 on the square root of 2. And lastly, to find the tan, I work out sine divided by cos. So I can say the tan of minus 45 degrees is sine divided by cos, and that is 1 on root 2 minus 1 on root 2 divided by 1 on root 2, and so I end up with minus 1 as my tan. And I presume if you put your calculator, get your calculator out and actually work tan of minus 45 degrees, it'll return minus 1. You could also, of course, come around here this way and see that it's the same as the tan of 315 degrees as well, if you wanted to. You could do that. Okay, so that's A and B. Let's now do C and D. So C/D. So, minus 120 degrees. So start at the positive x-axis, go minus 90, go another 30 degrees down here. And so it'll be something like this here. There is my point P. That angle is minus 120 degrees. So I need to find the x-coordinate and the y-coordinate of P. To find those coordinates, we could work with this right-angled triangle, sitting here. Or, in this case, I might actually use this one, or I could use this one sitting, dear me, who knows, sitting here. This one. Down like that. That angle sitting in there will be 60 degrees, sitting in there. So this angle sitting in here is also 60 degrees. So if in that triangle, here I have the hypotenuse is 1, has a radius of 1. Here's my 60 degrees, in this case, sitting here. And I'm going to call that side y and that side x0. As I said, it doesn't matter if you work with the first quadrant triangle or that triangle there, it doesn't matter. You'll get the same answer. And you can see that the sine of 60 degrees is equal to y0. And so from our special triangles, the sine of 60 degrees is the square root of 3 on 2. Likewise, cos of 60 degrees will be the adjacent over the hypotenuse, so that's x0. I suppose I should put over 1 over the hypotenuse. So x naught is the cos of 60, and the cos of 60 is a half. So now I have the coordinates of P, because when I look, the x coordinate of P is negative, the y coordinate of P is negative, so P has coordinates minus a half minus the square root of 3 on 2. And we can now go with our trig ratios. So the sine of minus 120 degrees is the y coordinate of P, which equals minus the square root of 3 on 2. The cosine of minus 120 degrees is the x coordinate of P, which will be minus a half. And the tan of minus 120 degrees is the sine divided by the cos, which will be minus the square root of 3 on 2 divided by minus a half, and that will come out to be plus the square root of 3. And in that case, I have my exact value, square root of 3. Your calculator would only give an approximation to that, I presume, 1.7 thereabouts. So, in the last example here, we worked out the exact value of the trig ratios for some negative angles. Of course, these ones worked out nicely because this was a 45 degrees and this was related to 30 degrees. 60 degrees, I should say. But most angles aren't that way inclined, and so when you get any other angle, you can only find approximate values, and you use your calculator, and lo and behold, your calculator's clever enough to do it. Okay, so in here, just get out your calculator, type in sine of minus 57, and when you do, whoops, you'll get something like 0.839 to 3 decimal places. You just used your calculator. So your calculator actually knows a fair bit of maths, which is good. Saves us having to work it out. And likewise, if I had to work out the cos of minus 112 degrees, put it in your calculator, and you get minus 0.375. And that's all you have to do. If you were thinking geometrically, minus 57 degrees is a fourth quadrant angle. Minus 112 would take you back into the third quadrant. So you've got a negative x value sitting there. That makes sense. Okay. Remember last time we actually had I said there's a whole lot of trigonometric identities that we could derive, and we had a look at some of them. I think I gave you about 6 of them, 6, 7, 8 I think in the end I talked about. Due to the clever way this thing's been redefined, all of these trig identities still hold. So everything that we had before still works. And as an example here, I said one of the trig identities had that was sine squared theta plus cos squared theta is equal to 1, and we showed that via our right angle triangles. Well, it still works here for any angle. So let me just show you that it still holds. So what I can do, for example, if I've got a circle, a unit circle, imagine that's a circle, use your imagination if you would. 1, 1, minus 1, minus 1. So this is the unit circle. Let's pick an angle, say, in the second quadrant, here. So there's angle theta. Here's point P. Okay. So I'll say for any angle theta, let P have the coordinates x0, y0. So, what do we know about x0 and y0? By definition, we know that x0 is the cosine of theta and y0 is the sine of theta. We know that x0 is the cosine of theta, that's by definition, and y0 is the sine of theta. The other thing we know is that P lies on the unit circle. I can say, but P lies on the unit circle. We know the equation of the unit circle. It's x squared plus y squared is equal to 1. And so we know that x0 squared plus y0 squared must equal to 1 because it satisfies the equation. That's what it means for a point to lie on that line, on that circle, I should say. And hence, cos squared theta plus sine squared theta must be equal to 1 because x0 is cos theta, y0 is sine theta. And so there is our trig identity, and it must hold for any angle, not just angles between 0 and 90. And we can do that for all the other trig identities as well. That sort of thing. Okay, so we now know how to find the values of the trig ratios for any angle whatsoever.